Do you feel ignorant because you don't know numbers? You don't know which one go which way and they got all these marks and things on them? I know, honey, it's hard, but there is a solution. Fort Bend Tutoring. And now here go Mr. Whitt. Explain math to us, Mr. Whitt.
Ladies and gentlemen, this is Mr. Whitt with Fort Bend Tutoring, and today's tutorial is going to be about solving systems of logarithmic equations. So we'll begin with a snapshot of the different types of problems that you'll see in this video. So check it out. I got number 1, number 2, number 3, number 4. And these are the type of problems that you can expect in this video. But don't think that I just have 4 problems for you. Oh no. Oh no. No, I actually have 10. Thank you. Yeah, there's 10 problems that I'll be going over with you in this video. So let's first of all revisit the different types of logarithmic properties that you'll see in this video. So we'll let a, b, m, and n be elements of the real number set, and a and b cannot equal to 1, and a, b, m, and n must be greater than 0. I say all that to say this. This first property right here is how we're going to convert from logarithmic form to exponential form. I'm pretty sure we'll be using that a lot. Then, as you move through these different properties, oh yeah, and there are quite a few, right? I mean, you already know there are quite a few, right? They're all here, and we'll be utilizing these in order to solve our systems of logarithmic equations. All right, so there you go. I just wanted to go ahead and put this page together for you, so at least if you weren't already aware of those, if you couldn't find it in your textbook, you got it right here, okay? So there you go. These are all the properties that we'll be using in this video in order to solve the logarithmic systems that we'll be tackling. All right, you got it? Good, let's get started. We have problem number 1. So our system has y equals the log in base 2 of x. We have y equals the log in base 4 of x plus 2. So one of the techniques that we'll use a lot in this video is the strategy of converting all of our logarithmic equations into exponential form. So for instance, with our first equation, this y equals log of base 2 of x, I'll be able to rewrite this as 2 to the y equals x. Yeah, this is the exponential conversion of that first equation. Looking at the conversion of our second equation, the y equals log of base 4 of the quantity x plus 2, we'll be able to rewrite this as 4 to the y equals 2x plus 2. So now that we have rewritten the equations in exponential form, let's go ahead and see how we can utilize this to our benefit. Well, for one, we know that x is equivalent to 2 to the y, right? I mean, it says it right here in this first equation. So why don't we manipulate this 4 to the y here in the second equation to see if that'll benefit us? For instance, I can show that 4 is equivalent to 2 squared raised to the y. Yeah. And that's using my exponential rules here. So basically, I'm showing that with a common base of 2, that 2 to the second power is equivalent to 4. And because it was initially raised to the y, well, it's still going to be raised to the y on the outside of the set of parentheses here. Now, using our exponential rules, that anytime you have a monomial raised to an exponent, that those exponents will multiply, then we can rewrite our second equation as 2 to the 2y equals to x plus 2. And even better, due to the commutative property of multiplication, I could show that this is 2 to the y raised to the second power. Now, you may be saying, well, Mr. Whitt, why did you go through all of that just to show that 2 to the y squared is equivalent to x plus 2? Well, the reason for that is because we know that 2 to the y equals x, and now I can substitute in the variable x for 2 to the y. Yeah, so let's do that. So I now have this equation rewritten as x squared equals x plus 2. I sure do. And once we set this equation equal to 0, we can now solve for x. So I'll be subtracting x and 2 to both sides of the equal sign. Yes, I will. And now I can rewrite the equation as x squared minus x minus 2 equals 0. And notice, we have a quadratic equation, and we can definitely solve this quadratic equation in many different ways. So of course you could use factoring. Yeah, you could do that, or you could go with the quadratic formula. Completing the square comes to mind. True. So I'm going to go with the easiest because I'm lazy. So I'll be using the zero factor property on this equation right here. So I can show that 2 factors of 2 that'll subtract to give me 1 are going to be 2 and 1. So we end up with the quantity of x minus 2 times x plus 1, this will equal 0. And then setting each one of these factors equal to 0, you'll have x minus 2 equal to 0, x plus 1 equal to 0. Solving for x in each equation, I'll be adding 2 to both sides of the equal sign in the first equation to get x equals 2. And then I'll be subtracting 1 to both sides of the equal sign, and I'll end up with x equals to negative 1, possibly. Because remember, there are going to be domain restrictions on your logarithms. You can never take the log of 0 or a negative number, because that will violate the function's domain restriction and make the equation undefined, and we don't want that. So we're going to definitely be aware of that as we plug these in order to solve for y. For instance, our first equation reads y equals log of base 2 of x, right? Well, we can't take the log of negative 1. We can't do it. It's undefined, so we won't be able to use negative 1 because it violates the domain of the function and makes the function undefined. So, therefore, x equals negative 1 is an extraneous solution. You won't be able to use it. So, we're going to say, no negative 1. You don't get to play here. Instead, let's see if 2 will work. So since 2 will be in the domain of both of the equations, we'll go ahead and attempt to use this to solve for the variable y. We know with the first equation we have y equals log of base 2 of x, right? Well, substituting our value of x with the number 2 right here, we'll have y equals log of base 2 of 2, which is, by the way, to the first power. So going back to the logarithmic properties that I showed you at the beginning of the video, we have a property that states that anytime the base of the logarithm and the base of the quantity is the exact same value, like in this case it's the number 2, that your result is going to be the exponent. So our answer is 1 for y. Our answer is 1 for y. In other words, we have found the point of intersection of the two logarithmic functions that are in our system. So if you were to look at the graph of the two logarithmic functions, you will see that they will intersect at the point 2, 1. And this is the answer for problem number 1, ladies and gentlemen. That's right. And if you've been with me for any given length of time, you know we're going to red box this answer. Red boxing it. That's it, ladies and gentlemen. That's the answer for problem number 1. Let's move on. Looking at problem number 2, we have the log of base 2 of x plus 3 times the log of base 2 of y equals 6. And the second equation is log of base 2 of x minus the log of base 2 of y equals to 2. Well, what I'm noticing right off the bat is that we have the ability to use the elimination method in this problem because the first terms in both equations are identical. So why don't we multiply the second equation by negative 1 in order to eliminate the terms that have the variable x? Yeah, that's the way I'm going to tackle this one. So we're going to have log base 2 of x plus 3 times log of base 2 of y equals 6 and end up with negative log base 2 of x plus log base 2 of y equals negative 2 for our second equation. Once I have this rewritten in this form, we can go ahead and use the elimination method, and what happens is our first terms, the terms that have the variable x, they cancel. They're additive inverses. So then, combining our remaining terms together, adding 3 log base 2 of y and log base 2 of y together, you'll end up with 4 log base 2 of y, which equals 4. From here, I'll be dividing both sides by 4. This gives us log base 2 of y equals 1. Once we have this, we can go ahead and convert this into exponential form and write the equation as 2 to the first power equals y. Well, we already know that 2 to the first power is just 2, so that means that we now have a value of 2 for our variable y. Yeah, it's 2, okay? So the variable y equals to 2. That's not a bad 2 right there, by the way. It's not bad. It's much prettier than this 2. And way better than that 2 right there, because that 2 is ugly, okay? It's an ugly 2. I'm proud of this one, though. All right, continuing on, let's go ahead and solve for x. Solve for x, we're going to plug our value of y into one of the original equations. And I think I'm going to choose the second equation because it looks easier. So plugging 2 in for y into the second equation, we'll end up with log base 2 of x minus log base 2 of 2 equals 2. Simplifying this second term, keep in mind that the base of 2 here is to the first power. So when I simplify this using our logarithmic properties, I can rewrite the equation as log base 2 of x minus 1 equals 2. From here, I'll be adding 1 to both sides of the equal sign. This allows me to rewrite the equation as log base 2 of x equals 3. From here, we can convert our logarithmic equation into exponential form to find that we'll have 2 to the third power equals x. Well, what is 2 to the third power? Oh, and that is an ugly 3. Oh, well, this will not stand. We have to fix that. A better 3. Okay, that's somewhat better. We're going to keep this 3 right here, okay, because it makes me feel better to keep this one, okay? So 2 to the third power, we know that means 2 times 2 times 2, and the answer is going to be 8, by the way, all right? So our value of x is 8, and that means that our solution to the problem, the point of intersection for this problem is 8, 2. If we were to plug 8 in for x and 2 in for y into the original system, both equations will give us a true statement, and that's how you know our solution is correct. I'm going to red box this. Red boxing it. That helps problem number 2. Next. In problem number 3, we have y equals log base 9 of x plus 1, and we also have y equals log base 9 of x plus 1/2. So since they already have y solved for in both of these equations, we may want to go ahead and use some substitution. Yeah. Let's see what happens if we were to set both values of y equal to each other. So I'll be rewriting the equation as log base 9 of the quantity x plus 1, and this equals log of base 9 of x plus 1/2. I'm going to then put all of our terms that have the variable x on one side of the equal sign, so that means I'll be subtracting log of base 9 of x to both sides of the equal sign, like so. And once I have this, I'll be rewriting the equation as log of base 9 of the quantity x plus 1 minus log of base 9 of x, and this equals 1/2, as those log of base 9 of x's cancel out on the right side of the equal sign. Now, using our logarithmic properties, we know that when we have the exact same base on our logarithms and we have subtraction going on, we have the difference of logarithms, we can combine this into log of base 9 of x plus 1 divided by x. Just like that. Yeah. So anytime you have subtraction, the difference of logarithms, it's going to end up being a fraction, a division problem. It's the quotient rule for logarithms. Bottom line. You start out with subtraction, you end up with a fraction, okay? It's kind of cute, isn't it? Oh, it's just me that thinks it's cute? Okay. From here, we're going to convert this logarithmic form into exponential notation. Oh, yes. Let's change this into an exponential equation here. So that means that I'll have 9 to the 1/2 power, and this equals x plus 1 divided by x. Yeah, just like that. Next, we'll show that 9 to the 1/2 power can be rewritten as 3 squared raised to the 1/2 power. Then multiplying your exponents 2 times 1/2, you'll end up with 3 to the first power, which is 3. So I now have 3 equals x plus 1 divided by x. And if you wanted to, you can show this as a proportion. Yeah, you could do that. You want to show this as a proportion? We'll have 3 over 1 equals to x plus 1 divided by x. And then you can just cross multiply from here, right? Using the extremes means method. And 3 times x gives you 3x. And 1 times the quantity of x plus 1 is just x plus 1. Oh, yes, it is. Yes, it is. And we'll subtract x to both sides of the equal sign. Are you subtracting with me? I hope so. Because you'll end up with 2x equals to 1. And then from here, I'm gonna take it over here. We'll have this 2x equals 1, right? We're going to divide both sides by 2, and that tells us that x equals 1/2. This is our value of x. Plugging in your value of x into one of the original equations will solve for your variable y. I'm going to choose the first one. So I'll have y equals log of base 9 of 1/2 plus 1. So this tells me that my value of y is going to be log of base 9 of 3/2. All right, and that's the result of me adding 1/2 plus 1. So as an exact value, this is my value of y. So that means that my point of intersection is going to be at 1/2 and log base 9 of 3/2. All right, so this is the exact value of y in our point that shows the intersection for the system for problem number 3. So we're going to red box it. Red boxing it. So the exact value of that log of base 9 of 3/2 or 1 5/10 is going to be approximately 185 thousandths. So there you go. All right, because I knew you were going to ask. Because I know half of y'all were going to be like, but Mr. Whitt, what's the real value though? So there you go. You see, you have it now. Okay, there it is. You don't have to ask. Here it is. Let's move on. In problem number 4, we have a system that reads the natural log of x equals 4 times the natural log of y. And the second equation reads log base 3 of x equals 2 plus 2 times log of base 3 of y. Yeah, that's a mouthful. So what I propose we do in our first equation is that we rewrite this and solve for one of the variables. If I take the first equation, which is the natural log of x, which equals to 4 times the natural log of y, I can rewrite this as the natural log of x equals the natural log of y to the 4th power. Well, the natural logs will cancel out so that I now know that x equals to y to the 4th power. So now that we have a variable x that equals to y to the 4th power, we'll be substituting y to the 4th power in for every x in this second equation. So it'll look like this. We'll have log base 3 of y to the 4th power equals 2 plus 2 times the log base 3 of y. Thus rewriting the second equation and substituting our value of x as y to the 4th power. Now I want all of the terms that have the variable y on the left side of the equal sign. So that means I'll be subtracting 2 log of base 3 of y to both sides of the equal sign here in order to isolate the terms that have my variable y. All right? So now we can rewrite our equation as log base 3 of y to the 4th power minus 2 log of base 3 of y, and this equals to 2. Just like that, because of course these additive inverses cancel out on the right side of the equal sign. And now it looks like we will eventually have an opportunity to use the quotient rule for logarithms. Because notice, they have the exact same base, that base 3, right? We have subtraction going on here, and you know this is about to become a fraction. But first, let's go ahead and move this coefficient of 2 as an exponent for our base y in this second term here. Okay? So that means that, rewriting it once again, a lot of rewriting going on, right? I mean, how many times do we have to rewrite this equation? I don't know. I mean, clearly we're rewriting equations over and over again. I mean, I enjoy it. I don't know about you, but I actually have fun doing that. I like manipulating the equation. So that being the case, we can now rewrite the left side using the quotient rule. So it becomes log base 3 of y to the 4th power divided by y squared, which equals to 2. Yeah, that's what we have. And did you know that y to the 4th power divided by y to the 2nd power is the same thing as y squared? So you'll end up with log of base 3 of y squared, which equals 2. Yeah, this is what you have there. Pretty nifty. If I say so myself. Next, we'll be rewriting our logarithmic equation into exponential form. So that means I have 3 squared equals y squared. And simplifying 3 squared to 9, we have 9 equals y squared. Well, according to the square root property, we'll end up with plus or minus the square root of 9, which equals to the square root of y squared, to get a value of y that equals to plus or minus 3. So currently our value of y could be -3 or it could be +3. However, we need to keep in mind the fact that the domain of logarithms, you can never take the log of a negative value or 0. So we need to keep that in mind, right? And looking back at our original equation, there's no way that we can take the logarithm of a negative value, of -3 in this case. So that means that our only possible solution for y is going to be y equals 3. Yeah, so even though this was equal to -3 or 3, we cannot use the -3 for y because it violates the domain of the original functions. So we'll be using the fact that y equals 3 in one of the forms of our original equation. And why do I say in one of the forms of our original equation? Well, it's because I'm lazy. That's why I say that. And I already know that x is equivalent to y to the fourth power. So why am I going back to an original problem to do the work all over again when that will involve so many steps? So I'll be plugging in our value of 3 for y and simplifying this because 3 to the fourth power is equivalent to 81. And 81 is our value for x, ladies and gentlemen. Oh yeah. It is. So our value of y is 3, our value of x is 81, and that means that our point of intersection is 81, 3. Oh yeah, that was fun. I enjoyed that problem. That system, yeah, it was a good one. I'm going to put a red box around this. Red box in it. That was problem number 4. In problem 5, we have log of base x of 2y equals 3, and we also have log of base x of 4y equals to 2. So we can begin in this case by converting both of these equations into exponential form. Let's see what we end up with. This first equation will give me x cubed equals 2y. The second equation will give me x squared equals 4y. Okay? If I solve for y in one of these equations, let's say the first one, I can start by dividing both sides by 2, and this tells me that y equals to 1/2 x cubed. Let's go ahead and plug in this value of y here, the 1/2 x cubed, into the second equation. That's what's about to happen. So we can rewrite this equation as x squared equals 4 times our value of y, which is 1/2 x cubed. Once we have this form of the equation, we can then say that half of 4 is 2, right? So this is now x squared equals 2x cubed. And then I'll be subtracting both sides by x squared in order to isolate the terms that contain my variable. So once we've subtracted x squared from both sides of the equal sign, we now have 2x cubed minus x squared equals 0. Now we'll use the zero factor property to solve this cubic equation. I'll be factoring out a GCF of x squared from both terms on the left side of the equal sign. So factoring out x squared, I'll end up with 2x minus 1 equals 0. And then setting both factors equal to 0 here, I have x squared equals 0, I have 2x minus 1 equal to 0, and then solving for both, we'll end up with x equals to 0, or adding 1 to both sides in the second equation. We now have 2x equals 1, and then dividing both sides by 2, we'll have x equals 1/2. All right. So remember that we're always concerned about the domain restrictions on our logarithmic functions. You cannot take the log of 0 or a negative number. Recall that we found that y was equivalent to 1/2 x cubed. Then plugging in 0 for x, we would find that y equals to 0. Our original equation states that log base x of 2y equals 3. Well, 2 times 0 is 0, and we can't take the logarithm of 0. That's not going to even happen. And even then, we would be in the base of 0. I don't even know if that's possible. So no, it's not going to be the case that we're going to be in base 0, and it's also not going to be the case that we can take the logarithm of 0. So that being the case, that's undefined. It's going to violate the function, and we will not be able to use x equal to 0 in so many ways. Okay. However, let's check out what happens with 1/2. Y equals 1/2 times 1/2 cubed. Well, 1/2 cubed is 1/8. And multiplying 1/2 times 1/8, you'll get 1/16. So 1/16 is the result for y, whereas x equals to 1/2. That means that our point of intersection is going to be at 1/2 1/16. And this is the answer for problem number 5. Red box in it. In number 6, we have y equals log of base 2 of the quantity x plus 28. I believe I'll be using substitution to solve it. I'll be plugging in this value of y into the second equation, or in other words, just setting these equations equal to one another. So it becomes log of base 2 of x plus 28. This equals 3 plus log of base 2 of x. All right, there we go. So I'm going to put all of the terms that contain my variable x on one side of the equal sign, which means I'll be subtracting log of base 2 of x to both sides of the equal sign. All right, we're going to make this all nice and pretty for you. Now rewriting our equation, we'll have log of base 2 of the quantity x plus 28 minus log of base 2 of x, and this is going to equal to 3 because our additive inverses on the right side of that equal sign will cancel. Because we have the difference of two logarithms with the same base, we can use the quotient rule. And in this case, that means I'll be rewriting this equation as log base 2 of the fraction x plus 28 over x, and that equals 3. Mind you, we currently have a logarithmic equation. So what I'll be doing next is converting this logarithmic equation into exponential form. So I end up with 2 to the third power equals x plus 28 divided by x. From here, I'll be rewriting our equation as a proportion. I know that 2 to the third power is equal to 2 times 2 times 2, which is 8, right? So I'll be able to rewrite this as 8 over 1 equals to x plus 28 divided by x. From here, I'll be utilizing the extremes means method, aka cross multiplying, to get 8x, which equals x plus 28, and then solving for x by subtracting x to both sides of the equal sign, and then rewriting the equation as 7x equals 28. From here, we'll be doing the division principle of equality and divide both sides by 7. This gives us x equals 4. Yeah. Does this violate the domain of our original equations? No, it doesn't. No, it doesn't at all. Yeah, you can plug in 4 all day long into either of those equations and you won't end up taking the log of 0 or a negative number. So that means that we can proceed. That's exactly what we'll do. So plugging in, let's say, 4 into one of the original equations, let's say the first one, you'll end up with y equaling log of base 2 of 4 plus 28, right? Well, this gives us y equals log of base 2 of 32. Well, because my base is 2 here, can I just go ahead and say that this is log base 2 of 2 to the 5th power? Yeah, I can do that, right? Because 2 to the 5th power is equivalent to 32. And so now, using my logarithmic property that says I can simplify this to 5, I know that y equals 5, ladies and gentlemen. Yeah, so remember, anytime that base and the base of the logarithm are identical, you can simplify that, aka cancel it out, and leave it with just the exponent. So your answer of y is 5. Was this not fun? Am I the only one here having fun here? I better not be the only one having fun on this problem, because this was a good problem. Oh, I enjoyed that thoroughly. So that means that my answer here, let's get this down on the page. It's 4, 5. Yeah, the point of intersection is at 4, 5. I know this. This will make a true statement in the original problem. So I'm going to be red boxing my answer. Red boxing it. All right, now it's problem number 6. Here we have problem number 7. We have y equals log of base 6 of x, and we have y equals negative log of base 6 of x plus 1. Well, in this problem, I will definitely be setting the equations equal to one another. Yeah, the y's are already solved for. I already have y solved for in each equation. I can just set these values equal to one another because y has equal to y. It has to. So that means that my equation is log base 6 of x equals negative log base 6 of x plus 1. All right? Recall that anytime you have a coefficient in front of a logarithm, it could become the exponent on the base here. Yeah. So this negative is going up here as an exponent. Oh, yeah. Here, I'm going to rewrite this as log base 6 of x equals log base 6 of x plus 1 to the negative first power. See, that's that negative 1 that became an exponent. It's negative 1 now as an exponent. You see that? Okay, great. Now, because we have a log set equal to another log, well, we're going to be able to cancel these out. Yeah, they're gone now. Anytime you have the exact same logs set equal to one another, it's over. Just cancel them out. Kill them. They're dead now. You'll end up with x equals x plus 1 to the negative first power. I'm going to rewrite the problem as a proportion. That's what I'm going to do. I'm going to have this rewritten as x over 1 equals 1 over x plus 1. And then I'll be cross multiplying to solve the problem. Okay? Those people that left at problem number 5, they don't even know what fun we're having right now. Go ahead and leave me a comment if you stayed to problem number 7, all right? Because I want to know that somebody else is having as much fun as I am right now. Let's go ahead and cross multiply, okay? We have x times x plus 1. I'm going to go ahead and just take my time with it. okay, just to show what I'm doing. I have x times the quantity of x plus 1, which equals 1 times 1, which is 1. We're going to distribute here. I got my arrows popping, okay? So I end up with x squared plus x equals 1, and then setting this equal to 0. You'll now have x squared plus x minus 1 equals 0. From here, we have a quadratic equation that is not factorable. That means that you'll need to use the quadratic equation on this, right? We're going to have an a value of 1, a b value of 1, and a c value of negative 1. My quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Plugging in our values for a, b, and c into the quadratic formula, we'll end up with negative 1 plus or minus the square root of 1 squared minus 4 times 1 times negative 1 all over 2 times 1. Just like that. Simplifying our result, we end up with negative 1 plus or minus the square root of 1 plus 4 all over 2. This gives us negative 1 plus or minus the square root of 5 divided by 2. And this is going to give us two possibilities for our value of x. Because the square root of 5 is more than 2, I know that the only solution that's not extraneous is going to be the solution that's positive. And that solution is negative 1 plus the square root of 5 divided by 2. I will not be able to use the negative 1 minus the square root of 5 divided by 2 because that's a negative value, and our original equation will want you to take the logarithm of that negative value, and that will make the function undefined. So we'll only be able to use this value for x. That's it. Okay, so here's our value for x. In order to find out the value of y, we'll be plugging this value in. So that means that our value of y will be equivalent to log base 6 of the quantity negative 1 plus the square root of 5 divided by 2. Therefore, needless to say, you'll need a calculator to get the true values for your x and y values. However, this is the exact solution of the problem. So we have our value for x, and this is our value for y. So our point of intersection is going to be at negative 1 plus the square root of 5 divided by 2. And our y value is log base 6 of that same quantity, negative 1 plus the square root of 5 divided by 2. And this is the answer for problem number 7. Remember, you'll need to plug in these values into your calculator to get an approximation of this point. All right, but this is the exact point right here. We're going to put a red box around this. Red box in it. And I'll go ahead and put the approximation as a point down here, okay, so that you'll have it. All right, let's continue. For problem number 8, we have log x squared equals to y plus 3, and we also have log x equals y minus 1. What I'll be doing in this problem here is I'll be starting by solving for y in one of the equations here. I'm going to go ahead and look at the second equation. So with the second equation, I have log of x equals y minus 1, and by the way, you should know that our base for the logarithm is base 10. When you don't see a visible base, you can assume that the base is 10. All right, so we end up with y equaling log of x plus 1. All right, so substituting this value of y into the first equation, we can rewrite our first equation as log of x squared equals log x plus 1 plus 3. So this is what I have thus far. I know that I can combine my like terms on the right side, so I can rewrite it as log x squared equals to log x plus 4. And then I want to put all the variables on one side of the equal sign. So I'll be subtracting log to both sides, like so. And I'll be also rewriting the equation as log of x squared minus log of x equals 4. And this is what I have thus far. I know that the quotient rule is about to be in play because I have two logarithms that have the exact same base that are subtracting. That means we can rewrite this as log of x squared over x, which equals to 4. Just like that. Then writing this result as an exponential equation, we'll have 10 to the 4th power equals x. Yeah, because we can simplify that x squared over x just to get x to the 1st power, right? So that means that x equals to 10,000. Just like that. What you think about that? Huh? So now that we know that x equals 10,000, let's go ahead and plug this in into where we have y isolated to find out our value of y. We know that y is equivalent to log x plus 1. And now that we know that our value of x is 10,000, plugging that in, we'll end up with y equals log 10,000 plus 1. And simplifying this, we can show that this is going to be log of 10 to the 4th power plus 1, knowing that the log and the base 10 will cancel out to just give us 4 plus 1, which equals to 5. So here is our value of y. So that means that our point of intersection is going to be 10,005. And that's it. Red box in it. That's problem number 8. Not bad at all. All right. Next to the last problem, ladies and gentlemen. We want to make sure that you guys are in a position to master a concept. And that's why our videos are usually longer than most videos that you'll find on YouTube, because 1 or 2 problems is just not going to cut it for you to fully grasp a concept. That's why we try to give you enough problems to actually sink your teeth into. So speaking about sinking your teeth into something, let's go ahead and sink your teeth into problem number 9. All right, so we already have the y solved for. We already know this, right? So I'm just going to go ahead and set these equations equal to one another. That's what I'm going to do. I'm going to rewrite it as log of 2x plus 4. Once again, paying attention to the fact that the base on the logarithms is 10. We're in base 10. And I want to put all the terms that have my variable in it on one side of the equal sign. So I'm going to subtract log of x minus 2 to both sides. Yes, I am. Oh, yes, I am. And I'll be ending up with the following result. I'll have log of the quantity 2x plus 4 minus log of the quantity x minus 2, and this equals 1. Because my logarithms have the exact same base, I can go ahead and use the quotient rule to rewrite this as log of 2x plus 4 divided by x minus 2, and this equals 1. Just like that. I'm going to go ahead and do a little something different. I'm going to exponentialize both sides of the equal sign, and I'll rewrite it as 10 to the log of this 2x plus 4 divided by x minus 2, and this will equal to 10 to the 1st power. So this is another method to solve a logarithmic equation. What will happen is on the left side, the base 10 and that logarithm will cancel out to give you 2x plus 4 divided by x minus 2, and then of course 10 to the 1st power is just 10. So I'm going to write this as 10 over 1, knowing that I'm going to want to end up with, let me go ahead and put that in view, sorry, because I know that I want to end up with a proportion as far as my preferred method of solving the equation. Solving our proportion here, I'm going to be cross multiplying, of course. I'll have 2x plus 4 equals 10 times the quantity of x minus 2. I will then get my arrows popping. So I'll bring down the 2x plus 4, which equals 10x minus 20, and then solving for x by subtracting 2x to both sides as well as adding 20 to both sides here, we'll have the following results. We'll have 24 equals 8x, and then we'll be dividing both sides by 8, which will give us a value of 3 for x. All right? So 3 is definitely something that we can use in the original equations. So that means that I'll be plugging in 3 into one of the equations to solve for y. And as a matter of fact, we'll use that first equation to solve for y. So we'll have y equals log of 2 times 3 plus 4. Okay? So what does that do for us? That gives us y equals the log of 10. All right, because that 2 times 3 is 6, 6 plus 4 is 10. And now, ladies and gentlemen, what will happen is this will simplify to give us 1. Why? Because the exponent on that base of 10 is 1, and since those bases are identical, they'll cancel out to leave you your exponent, which is 1. That means that our answer for this problem, for problem number 9, is 3, 1. Red box in it. So here we have our final problem, problem number 10. So we have log x plus 2 log y equals 5, as well as 2 log x minus log y equals 0. So what we can do in this problem is we can actually use the elimination method. So with the elimination method, I'm going to be eliminating the terms that have the variable y. And I'm going to do that by multiplying the entire second equation by 2. So this will allow me to rewrite the system as log x plus 2 log y equals 5. And now this second equation reads 4 log x minus 2 log y equals 0. So, using the elimination method, adding these equations together, my y terms will cancel out and I'll bring down 5 log x equals 5. From here, we can divide both sides by 5. This gives us log x equals 1. And then if I were to choose to exponentialize both sides of the equation, I'll have 10 to the log x equals 10 to the first power. Of course, the base 10 and the log will cancel out to give me x equals 10 to the first power, which is 10. So I now know that x equals 10. So now I'll be plugging this 10 into one of the original equations. And I believe I'm going to use the first equation. I'll have log 10 plus 2 log y. This equals 5. We know that log 10, because 10 is to the first power, is equivalent to 1. That's because these cancel out and just leave you the exponent, right? So continuing to bring down my equation, I have 1 plus the 2 log y equals 5, and it's this equation that I can solve for that'll give me my value of y. Let's start solving this equation by isolating the term with the variable. So I'm going to subtract 1 to both sides of the equal sign here. All right, my 1's cancel out. I'll be bringing down 2 log y equals 4. I'm going to then divide both sides by 2. Dividing both sides by 2 gives us log y equals 2. From here, I'm going to exponentialize both sides of the equation to get 10 to the log y equals 10 squared. The 10 and the log will cancel out, so I'll have y equals to 10 squared, and that value is 100. So y equals to 100. So that means that my point of intersection here is going to be 10, 100. That's the point where these two functions intersect. And now we're going to red box it. Red boxing it. Just like that. So ladies and gentlemen, this now completes systems of logarithmic equations with me, Mr. Whitt, and Fort Bend Tutoring, FBT. And as always, please rate, comment, and subscribe. And if you're able, please donate, as that helps us bring you more free math tutorials from Fort Bend Tutoring. Peace.
We certainly hope you enjoyed today's presentation by Fort Bend Tutoring. Did you understand the program? Would you like to rate us or give us some feedback or subscribe to us? You could do all that on tutormemath.net. Leave a nice comment. Don't just leave something ignorant on there. If you didn't understand the lesson, ask the professor to explain it for you. Don't just get mad and write something ignorant on there.
It's over. It's over. I know you were expecting more, but it's done. No. Calm down. It's okay. It's over now. I'm going to put a red box around this. Red boxing it.